Hello, this is the first video in a playlist that I'm calling Complex Variables. And I'm not simply calling it complex numbers because we're going to do much more than complex numbers. Of course, we're going to look at properties, definitions, prove a lot of the properties of complex numbers, but we're also going to take functions of complex numbers, limits, continuity, differentiation, integration. So it's going to be a pretty rich playlist on complex variables. But today's topic is just complex numbers. And so we're going to build it up and look at the real number system first. And so the integers are part of the real number system, and they take on the numbers of the form, -2, -1, 0, 1, 2. And they're called integers, and they're denoted by this script Z, capital Z. So if we let A and B be integers, and we note that the sum of two integers and the product of two integers, now usually you just write it AB, but sometimes you put the multiplication sign in the middle to be explicit, of two integers is also an integer. And so that means A plus B is an integer itself. And so is A times B. And this property is called closure. So the set of integers are closed under the binary operations addition and multiplication. Rational numbers, numbers that can be represented in a fraction, A over B, are called rational numbers, and it's denoted by the script Q. Rational numbers are solutions to the equation bx equal A, right? Divide both sides by B, you get x equal AB. Now, where, A and B are integers. Now, which leads to the concept of division, right? Dividing by both sides, dividing B to both sides. And we're not going to delve into the real number system unless we have to in later videos. And note that the integers are a subset of the rationals, right? If we let A as an integer, and if we just let B equal 1, then we're back in the integers. Now, irrational numbers, and they're just numbers that are not rational, and they're called irrational. And it's denoted by R minus Q. Now, there's not a universally accepted letter for irrational. Some might use a script I or a script P, but R minus Q is always denotes the irrationals. Now, R is the real numbers. Of course, we haven't defined it yet, so it's kind of a circular definition. But and Q is the rationals. So we take the real, subtract out the rationals, and we get the irrationals. So for example, square root of 2, this cannot be expressed in a fraction form or pi. The real numbers comprise of the union of both the rational and irrational numbers denoted by script R. Now, the real numbers can be represented on a real number line. So every dot on a line can represent a real number. Now, here's a quote that I absolutely love. I don't know, it's not my quote, and I actually don't know whose quote it is. So if you know, put it in the comments. But if you look up in the sky at night and you see the stars and the blackness between the stars represent the rational numbers, and the blackness between represents the irrational numbers. That's how dense the irrational numbers are. Now, the complex number system, since there's no real solution, x to the polynomial equation x squared plus 1 equals 0, then thus complex numbers, which are denoted by the script C, were discovered. Some say invented, some say discovered. That's your preference there. Complex numbers have the form Z is equal to A plus IB. Now, some like to put the I behind the B, so A plus BI. Both are okay, and we'll use both notations. And A and B are real numbers. Now, I is called the imaginary unit, and it has the property that I squared is equal to -1. Now, of this complex number, A equals BI, A is called the real part of Z, and it's denoted by R of Z. It's the real part of Z. And B, it's called the imaginary part of Z. And this is a script I, so I of Z is the imaginary part of Z. And we'll use these functions sprinkled throughout this whole playlist. Now note that R is a subset of the complex numbers when B is 0. So if we have a complex number, A plus BI, if we set B to be 0, then we just have A, but A is a real number. And so A is a subset of the complex numbers. Now the conjugate, also called the complex conjugate of a complex number Z, so Z is equal to A plus BI, it's complex conjugate and you put a bar above it, you just A minus BI. So whatever this sign is, you take the opposite, and that's called the complex conjugate. Now sometimes it's denoted by a superscript asterisk. So Z asterisk, that's complex conjugate. Now operations with complex numbers. So addition of two complex numbers, Z1 and Z2. So if Z1 is A plus BI and Z2 is C plus DI. Now really we don't need the parentheses, but that's just to illustrate that this is a complex number and this is a complex number. So it comes down, and then you add the real parts and you add the imaginary part or components, and then this is the new complex number. Subtraction works very similar. If we subtract two complex numbers, we essentially subtract the real part and then subtract the imaginary part, and then that's the new complex number. Multiplication of two complex numbers, so Z1 times Z2 would be in this form. And the process is the FOIL method, first, outer, inner, last. You take A times C, A times DI, and then you take BI times C, and BI times DI. And now we combine terms. Now notice that I squared is minus 1, so it changes the sign. And then it's a real component or real part of this number, right? The I goes away. So you combine the real components and then you combine the imaginary components, and then this is your new complex number. Division, so Z1 divided by Z2. So we divide two complex numbers. The way that we think about this is we first multiply it by 1, and that is the complex conjugate of the denominator divided by itself. And so we haven't changed it, but writing it in notational form, we get this. Now this is the product of two complex numbers, so we FOIL it out. So in the denominator, C times C is C squared, and then the interaction term vanishes and we get D squared minus I squared. And then if we FOIL the numerator, we combine the real part and the imaginary part over C squared plus D squared. But then we take the denominator times, we divide it by each term and we get this. But then this is the form of a complex number, right? So we're taking multiplication, addition, division of real numbers, we get a real number. Same way here. So this is the new complex number after we take, the division of two complex numbers. Now, an interesting note, or at least I think it's interesting, if we set B and C equal to 0 and A and D equal to 1 in this formula, then it's really easy to show 1 over I is equal to minus I. And this is a formula that we'll, again, use throughout this playlist. R has a whole library of complex numbers just in the base. So we create a complex number of 3 plus 4i. We just take two real numbers, an I, and so this I've created a vector of complex numbers. Or you can assign them individually. So Z1 is 3 plus 4i, Z2 is 5 plus 12i. You can add them and you get this number. You can subtract them. And if you use the formulas above, you'll see that you do indeed get these numbers. The multiplication of two complex numbers, the division of two complex numbers. You can extract the real component. So Z1, let's go back, is 3 plus 4i. So the real component of Z1 is 3. The imaginary component of Z1 is 4. The complex conjugate it just negates that middle term. So z1 was 3 plus 4i. Its complex conjugate is 3 minus 4i. We can plot complex numbers. So z was this vector of complex numbers. So if we plot z, it automatically creates the Cartesian coordinate system and puts those dots. And then I use the arrows function to create little vectors. And let me show you what this is on the next page. So the plot function creates those dots. And many people think of them as just dots in this two-dimensional plane where the abscissa is the real component and the ordinate is the imaginary component. Sometimes it's advantageous to think of them as vectors originating from the origin. And so this is another representation. Okay, so I wanted to keep these 10 minutes or less, so I'm at time. So hope you enjoyed this. If I sure did, please like the video and subscribe so you don't miss the next one. Thanks, bye.